Good afternoon, everybody. My name is Soria Petran. I'm a senior researcher in the National Institute for Building Research in Bucharest, Romania. And I'm leading the cluster for promoting nearly zero energy buildings in Romania. And together with my co-panel leader, Kurt Emil Eriksen from Velix, we are welcome you to this second session of the panel 8 buildings, which is focused on nudging consumers to create good indoor comfort at low use of energy. We have a very nice lineup of speakers. First of all, will be a presenter, Mr. Mark Groslost from Institute Wohnen und Umwelt from Germany. Then we will have Sahar Zahiri from Oxford Brookes University, together with Rajat Gupta presenting for a professor at the same university. And then we will have Margot de Paul from Kenning Centrum Energie under the Thomas More University of Applied Science in Belgium. And then from San Francisco, Ami Amarna from Senior Technical Executive in the Electric Power Research Institute in Palo Alto. We have a very nice set of presentations that I'm looking forward to hear. They will coming under the same umbrella, under the same topic, but they are from different perspectives. So, Kurt, if you want to add something. First of all, we will have, sorry, because I forgot to mention this. All the presentations are recorded, and we will have all the speakers for us for a 5 minutes question and answer session after each presentation. And also we will have some minutes at the end for some additional questions. Please do not hesitate to put at any moment the questions in Huva section question and answers, and we will manage to pass to the speakers during the question and answer session. So thank you very much. Kurt, if you want to add something.
Only welcome to this session. I think you did it tremendously good, Horia. So let's just start.
Yeah, so the first speaker, Mark Groslost, will present the Consume and Pay Less, a budget approach for running costs in social housing.
How could we achieve to consume less resources like energy or drinking water and pay less money for living? Hello, my name is Mark Groslost. I'm Scientific Associate at the Institute for Housing and Environment in Darmstadt, Germany. And I'd like to present you a project where an existing and a new building were using a budget approach for reducing running costs and a climate-friendly living in social housing. The project was funded by the German Ministry for Economy and Energy. So what are the challenges we are facing? Climate protection needs the support of all groups of society, rich people, the middle class, and also poor people. But poor people don't have the money to live in energy-efficient houses. The rents are normally too high. Low building standards in combination with poverty or fuel poverty can lead also to low room temperatures, and this leads to an increased risks for illnesses like respiration diseases. And finally, ancillary and running costs can reach at last half of the rents and can overwhelm the poor people financially. These issues should be eliminated by the Passive House Social Plus from an organization called Neue Wohnraumhilfe in Darmstadt. The Passive House Social Plus combines low rents, low ancillary and running costs with climate protection and high living standards in social housing. The goals of the Passive House Social Plus were to build inexpensive flats for affordable living, to have a significant reduction in ancillary costs like for heating, electricity, or also for internet, have a high energy efficiency for the building envelope, hot water preparation, household electricity, and system technology. The use of treated grey water to flush the toilets, photovoltaics and battery storage, a flat rate rent for most of the ancillary costs, including heating and domestic hot water preparation, and also a budget for drinking water and household electricity, which are included in the rent, and finally a visualization of the consumption and the budget for the tenants. Now I'd like to show you some pictures of the project. The building is situated on a former US Army military site. Here on the picture you can see the building before the retrofit. It consists of 3 stories and has 3 entrances. And 2 of the 3 entrances were retrofitted with passive house components. And the 3rd entrance was removed and replaced by a new building in passive house standard. In total we have 42 flats, and flats in the new buildings are barrier free, and there are also 6 wheelchair accessible flats. In total we have 3,235 square meters of living area. At the beginning, the existing building was dismantled until the building shell. A new top story was added to increase the living space. The building envelope was thermally insulated, and each flat has its own ventilation system with heat recovery. You can see the existing building after the retrofit. On the right side, you can see on the roof of the building the photovoltaic system. The new building was constructed as a passive house directly on the ground without a basement, and it has also in each flat a ventilation system with heat recovery. Here's the new building from the south side after the works were finished. Here are some impressions from the interior of the buildings. On the left side, a view of the barrier-free bathroom, and on the right side, a view at a kitchen which is pre-installed from the landlord with very energy-efficient kitchen appliances, and also LED lighting which is in every room to reduce energy consumption. As already mentioned, both buildings have PV systems. The existing building about 40 kilowatt peak power on the roof and a battery storage of 18 kilowatt hours. The new building has about 44 kilowatt peak power PV and a much bigger battery with 43 kilowatt hours. Another important issue of this project is the grey water system. Slightly polluted water from the showers is collected separately, then filtered in the basement and treated biologically, and the cleaned water is then used for flushing the toilets and so reducing the consumption of drinking water. For the accounting, almost all ancillary costs are charged as a flat rate. Also the costs for heating and domestic hot water according to a German legislation. The costs for water and household electricity are not included as a flat rate but as a budget. And this budget is calculated so that an economical household can get along with it. And the amount of the budget is calculated by the number of people in the apartment and if the budget is exceeded, the tenants have to purchase an additional quantity. There are also displays in the apartments for the tenants to know how much of the budget they have used till now. Here you can see one screen of the display showing on the left side the budget for electricity and on the right side the budget for domestic water. If the budget is exceeded, the tenants get a warning and a calculation how much they probably must purchase. The buildings were finished in 2019, and now I'd like to show you some results from the measurement for the existing building. The mean room temperature in wintertime was 22 degrees Celsius, which is comparable with other energy efficient buildings, even if they have a heat billing. The measured energy for heating, including distribution losses, was 21.3 kilowatt hours per square meter and year, which is quite low. For domestic hot water, we measured 17.8 kilowatt hours per square meter, and the total consumption for district heating, including all losses in the building, were 48.9 kilowatt hours per square meter. The grey water cover ratio for flushing the toilets was only 20 to 40% at the beginning. But last summer, a new filter was added, and after that, the cover ratio rose on values greater than 60%. The drinking water consumption without the water for flushing the toilets was 21 cubic meter per person and year, which is 28% below the comparable mean value in Germany. And the PV system, in combination with the battery storage, has a cover of 40% of the building's electricity consumption. For household electricity, I'd like to show you some detailed results. Here in this diagram, you can see on the x-axis the power budget per flat, and on the y-axis the power consumption per flat. And the bisecting dotted line shows those points where budget and consumption are equal. Now you can see the results of the 22 flats as dots. Some are below the dotted line, which means that the consumption is below the calculated budget, and some are above. In mean, the budget is exceeded only by 2%, which is really remarkable because it was calculated according to the best energy efficient standard in Germany for electricity, the Class A. So in total, the household electricity consumption is very low. Now I'd like to summarize the main results of the project. We have high energy standard in combination with a ventilation system as base for healthy living for the tenants. The rents are at €6.50 per square meter and month, are well below comparable rents in the same city, which are above €10 per square meter and month. The ancillary costs are 45% below those of comparable users in the same city. And we have, despite the flat rate billing for heat and domestic hot water, very low heat consumption. The budgets for drinking water and household electricity are only slightly exceeded, so the approaches for reducing consumption and costs seem to work also in social housing. Now I'm at the end of my presentation, and I'm looking forward to your questions.
I would like to start, if it is okay. I have a general question. And it's regarding the to set up this system. Do you think that it would be possible to have all the energy suppliers throughout Europe or throughout the world or throughout a city to work with such a system here? Because I think you have proven that it works. But I think the big challenge is to have the energy suppliers to buy in for it. Have you had any considerations about that?
At this region, we have district heating. So every house has to be connected to the district heating. And there's no question that the landlord has to use this energy source. Of course, in other regions, you don't have the same kind of energy sources, and maybe other solutions are cheaper. As discussed in other sessions this morning, maybe in another region, heat pumps maybe are financially more welcome, but this is a question of every special project. In general, when you are reducing the energy consumption, as with passive houses, with nearly zero energy houses, all the houses have low consumption. So this is not a special topic of this building or this project.
Thanks.
And we have additional questions from the attendees. First of all, it is appreciated as a very impressive result obtained. And the question is, how could the social housing body fund such a comprehensive renovation?
This is maybe a special thing in Germany, but as I know, in Austria, for example, there's also state funding for social housing. And the funding was not exceeded over the standard funding for social housing in Germany, except for the special technique for the budgeting visualization technique. But this house got the same funding as every other building company building social houses in Germany. But the approach was to reduce building costs, and in this region, to build a dwelling with €6.50 per month in square meters rent is challenging, but they really managed this challenge.
You mean to reduce the operation costs?
No, to reduce the building cost, the construction cost.
The construction cost, okay. Okay. And the project seems to have been very successful. Many retrofits projects do not deliver the expected savings. Do you know what works so well here? Is the information system for tenants an important factor? And I will add a small question to that. The warning system informing the over consumption to the tenants. Is this only when the consumption, the estimated consumption is over? It's going more, or it's before, based on an estimation consumption based on metering in the last period?
Yeah, I'm going to answer the second question first. I think, yes, there's a warning when the tenants are probably to reach the budget, and when that budget's actually used for the current month, they get this information, so they have till the rest of the year the possibility to to change their behavior and to reduce consumption, that they don't have to pay additional money for water or electricity. And the first question is why it seems to work very well. And I think there are a lot of reasons for that. First of all, the architects were very engaged when constructing the building. So we have a building which is really nearly constructed exactly like it was planned. Second thing, that in the usage phase, the first 1.5 years now, the building owner, the architects, and also we as a scientific support are looking if is everything going well? Is there something to optimize? And this is, I think, quite important to have an optimization after the tenants move in. This is the base to get really good results in energy efficient projects.
Okay, thank you very much for the clarifications. And I think it's time for the next presentation, which will be given by Sahar Zahiri, a natural experiment to measure change in energy use and indoor environment in dwellings with smart heat pump retrofits.
Hello, my name is Sahar Zahiri from Oxford Brookes University. Welcome to this presentation. In the next 15 minutes, I'm going to talk about natural experiment that was carried out to measure changes in indoor environment and electricity use in dwellings in Oxford in the UK after installation of smart heat pumps. In this presentation, I'm going to give some backgrounds and context regarding the UK government target to accelerate the path to net zero and installation of heat pumps. I will also provide insight into study objectives and methods and characteristic of case study dwellings, followed by results and findings and final discussion. Moving to background and context, to accelerate the path to net zero, the UK government announced its 10-point plan for green industrial revolution in 2020, which includes a challenging target to install 600,000 heat pumps per year by the end of 2028. In addition, 90 million heat pumps need to be installed across the country by 2050, which will be a step change the 20,000 heat pumps unit that are currently being deployed across the country every year. To achieve this target successfully, it's important to balance electricity demand and supply locally, which will also avoid the expected surge in heat pumps installation to exceed the capacity of the current UK electricity system. In addition, deploying smart heating controls coupled with heat pumps can also help with local grid balancing while maintaining comfort of the resident. With this context, and also as I mentioned earlier, this study used a natural experiment approach to get insight into changes in indoor environment and electricity use, pre and post heat pump installation across 9 social housing dwellings in Oxford from October 2020 to December 2020. The study used a mixed method approach, included household survey to identify social demographics and ways residents heat their homes, physical characteristics using energy performance certificate data before heat pump installation, and monitoring of indoor temperature and relative humidity in 9 dwellings with 15 minutes interval using Bluetooth-enabled hobo data loggers that were located in living rooms of each dwelling. Electricity use was also monitored in 2 dwellings with 15 minutes interval using loop device, which was connected to electricity meter of each dwelling. The 9 dwellings included 5 bungalows and 4 flats located in socially deprived area in Oxford. From EPC certificates, higher energy rating in flats were identified compared to bungalows with EPC of D and C. This was possibly due to the lower exposed area in flats compared to the bungalows. EPC data also showed higher predicted heating demand in bungalows compared to flats before heat pumps. And in order to improve energy efficiency of bungalows, field cavity walls were installed following the installation of heat pumps in autumn 2020. Studying the household characteristics showed no association between annual income and annual energy cost, although all dwellings had single occupancy and the average annual income of the resident was less than £15,000. Similarly, there was no correlation between predicted heating demand that obtained from EPC and annual energy cost self-reported by residents, although all dwellings have similar size and occupancy. This confirmed the impact of residents' behavior on energy use as compared to dwellings characteristic and household characteristic. This can also be an implication for local authorities and energy companies who use EPC to target dwellings for energy retrofits for the future across the country. Studying environmental monitoring data across 9 dwellings shows interesting result. Significant increase observed in indoor temperature in bungalows after heat pump installation. This was due to the improved air tightness along with constant heating as compared to flats. The mean indoor temperature in bungalows also increased to 23.4 degrees Celsius after heat pump from 20.4 degrees Celsius pre-heat pump.
I think we faced a technical problem. But taking to the fact that we are all here and Mark is all here, I would like to ask another question. Not sure if I understood this well. Did the social housing body increase the rent for these dwellings? And if so, did it lead to a renewal of the tenants?
No, the buildings, that was another question. Buildings were empty before retrofit because it was a former army site. So in 2019, all tenants moved in, and since then there was no change of tenants till now. So the project is quite new, and there was no renewal of tenants, but also we had of course another different type of users, but that's not because of the refurbishment.
Okay, thank you very much. Let's go back to the presentation.
and ranging extremely low to extremely high. However, after installation of heat pumps, due to the continuous heating as indicated by higher indoor temperature, indoor relative humidity reduced significantly in bungalows compared to the flats. The changes in indoor relative humidity in flats was subtle, in line with minor changes in indoor air temperature after heat pump installation. Moving to next slide regarding electricity use analysis. An increase in daily electricity use identified across the dwellings after installation of heat pump. This was due to the colder weather and constant heating. In addition, daily electricity use in flats after heat pump was lower compared to bungalows. This was also due to the residents' preferences to keep the windows open when the heating was on, which was observed during the site visits. To assess the efficiency of the heat pumps and account the weather, electricity use was also normalized for outdoor temperature, showing 49% reduction after heat pump installation. This confirms the efficient running of the heat pumps despite the user preferences. In addition, mean daily indoor temperature and electricity use profiles showed rise in electricity use during the peak periods from 4 p.m. to 7 p.m. This reinforced the need to integrate time of use tariff to encourage load shifting amongst the residents. It's also worth noting that despite more distributed electricity use during daytime after heat pump installation, it's important to utilize renewable electricity locally for grid balancing and to reduce network pressure. And finally, to sum up the findings which were discussed in this presentation, we can conclude that indoor temperatures were more stable after installation of heat pumps across the dwellings. However, wide variation of indoor temperature ranges identified across the dwellings, despite having similar size, number of the occupants and occupancy patterns. As compared to the flats, bungalows experience excessively high indoor temperature of 25 degrees Celsius above, and consequently low indoor relative humidity due to the improved air tightness as a result of cavity wall insulation, continuous heating, and limited windows opening. Since no correlation identified between annual energy cost observed by the resident, mentioned by the resident and EPC rating, it's important to obtain details about occupancy characteristic when data for EPC rating are collected. An increase on electricity used for heating during the evening peak, especially after heat pump installation, make a strong case for connecting these dwellings to time of use tariff with different prices during the peak and off-peak periods, which is in line with wholesale prices. However, since this can introduce automation and complexity for residents, it's important to strengthen the engagement with residents and improve their knowledge and understanding on low carbon heating and time of use tariff to get the best benefits of heat pump installation and smart heating control. And thank you very much for listening.
It was a very interesting presentation. There's a lot of findings as I see it, I have one question about the option to optimize buildings, because if I understood you correctly, the indoor temperature rised after the renovation, after the heat pump was installed. Have you thought about any solutions which could optimize the use of the building so that we avoid that? And it's
Yes.
not only costs. It's not only saying that, okay, if I ask you to pay a little bit more per kilowatt hour during the daytime, then I'm forcing you to reduce your indoor temperature. But it's another solution. Have you been thinking about other solutions?
Yes, I mean, some of the issues, as we also mentioned in the presentation and we identified, was relating to the occupants' behavior. And the other thing, the increase on temperature was mostly in the bungalows compared to the flat, which was related to installation of the improvement in building insulation on cavity walls. So we need to train the residents to use, one of the solutions is to train the resident in order to use make a good sense of using smart control, and you know how to use the constant low temperature of the heating rather than just turn it on and off, so they can have more better indoor environment.
Yeah, and just to add to what Sahar said, I think it's a really good point that you've raised. I think there is a bit of tension between this drive to have on-demand heating versus constantly on low temperature emitting heating. And that some of that is happening because the smart controls were really designed to offer ease of use. The tenants ended up using those controls to drive up the set point temperature very quickly because they were noticing that not enough heat was coming through. In response to what could be done, I think the smart controls do have a second phase where they are going to look at optimizing heating in relation to resident preferences, outdoor weather, indoor temperatures, and price signals. That's really the next phase of the study. And we are really looking forward to it as to what happens then when this process gets automated more, and how do the tenants react to that.
Thanks. Maria, are you here with us?
Yes, I'm here, obviously.
Yeah, okay.
I'm just picking up the last question. With the study of bungalows, there is a possibility of some occupants having chronic health issues. Was there any qualitative work done on perceived comfort levels and health outcomes of the stable temperature?
At the moment, regarding the comfort, we just did monitoring analysis and record indoor temperature and humidity. But in the future, we are going to carry out some interview and survey with the occupants, which might be answer this question.
Yeah. No, I think this is a fair point that we will look at the relationship between, the retrofit and health benefits through the household interviews that we'll be conducting. It will be self-reported health. So we are not going to take physiological measurements, but we will definitely ask about improvements in health. Just to be clear, the heating system prior to the heat pump was very inefficient night storage heaters that most of the occupants were fed up with. So you can also imagine that it was also some of the unmet need for heating that was probably met through the heat pump. So having more stable temperatures is actually not a bad thing, even if they're slightly high, because they were probably being underheated before, which also has a health implication given the age of the occupants. So yes. So short answer is we will explore it, and there is certainly something there, I think.
And how would you explain the difference with the EPC from the measurements? despite the behavior of the occupant? Maybe the calculation methods or the input data?
Yeah, this is a matter of concern actually, because essentially what we are finding is that self-reported heating costs have no bearing to what the EPC of the property is. And this is possibly happening because the EPCs are created with very rough and ready data that you can quickly get, gather and create an EPC with very little contextual data about occupancy characteristics, about occupant preferences, behaviors. And our suggestion is that when these EPCs are being created and data are being gathered, parallel surveys are done about occupants and occupancy characteristics to feed that into EPCs as well, so that there's more contextual data. Because the concern here is that if local authorities are planning for large-scale retrofits using, low EPCs, which is fine, but it might be that there are some high EPCs, which are C or a D or even B, but have higher energy costs, which are not getting captured. So we might be missing those homes. So I think we are saying that you need both. And I know there is a lot of work going on in UK now to link EPCs with real data and not just model data. And I think that certainly needs more investigation. Sahar, if you want to add something.
No, thanks. You covered everything. Thanks.
Okay, thank you very much for the presentation and for the discussion. And I think it's time to jump into the next presentation from Margot Dipau. It's about a study into the practical usability of sustainable cooling systems for the indoor summer comfort.
This presentation is about the practical usability of sustainable. We know that there is an increasing demand for cooling, even in residential buildings. And sustainable cooling systems are often not applied because there is a lack of performance data, because there is a lack of guidelines for selection and dimensioning of those systems. So that's why we started schools. It's a research project. It stands for Sustainable Cooling Systems. And we want to give insight in the performance of those systems by means of measurements and simulations. And the main result of schools is in fact a decision support tool for sustainable cooling systems. So I will first show the tool, but as it is based on simulations, at the same time, it gives the scope of the simulations. Then I will go a bit into detail on the definition of comfort classes, and then ending with some general results of the simulations and a conclusion. So this is what the decision support tool looks like. At the left side, we have some building parameters to select. At the right side, we have results. On the x-axis, there are different cooling systems, and on the y-axis, so the height of the bars stands for the energy consumption for cooling. And the color of the bars gives an indication of the comfort. And then we see that the left bar is for the day zone and the right bar is for the night zone. Then I will go quickly through those building parameters. First, we have to select a building type or a building typology. We have 5 fixed typologies for residential buildings. So it means that we work with given building plans, so that makes it user-friendly. But of course, in that way, it's not possible to evaluate your own specific case. Then we also can choose the thermal mass. We can choose between massive or light-weight. Installation level, we work with new buildings, so we can choose between the current EPB standard or passive building level. For some building typologies, we can also choose for a higher window percentage than what is on the building plans. And then, of course, we can change the orientation of the building. And then finally, we also can apply some passive cooling strategies. The first is sun protection. So we can choose between no sun protection, external screens on all windows, or sun protection natural ventilative cooling. So the first option is with small window openings, which are in fact burglar proof. And then we have another option with intensive ventilative cooling with large window openings, where you will need some grills or something like that. Then when you have selected all your building parameters, you can go to the results for different cooling systems, like I said, but in fact, focus is on the emitter. You can see it on this listing of the cooling systems that we considered. First of all, we have some systems on the ventilation, like adiabatic cooling on the return of the ventilation unit. And we also have cooling coils in the supply air of the ventilation, one at high temperature and one at low temperature. We also have some hydronic systems. First of all, two convective cooling systems, one with capacity of 15 watt per square meters. The idea is that it's a convective system that is connected to a geothermal source, and that is principally dimensioned based on the heat demand. So that's why the power for cooling is limited. But we also consider a convective system with almost unlimited cooling power. So going to 50 watt per square meters, it represents, for instance, an active cooling system, where there is not really a restriction on the capacity. And then we have two types of floor cooling. First one is a light system. The second one heavy, so with the pipes in the concrete. But you can see they also have different power, 20 and 30. There are also differences in insulation. So the idea was to have two different types, and we see in the results that there is not really a difference or an important difference between the two types. Then I come back to those comfort classes. The idea was to work with colors. So green means that there is good comfort, and then going to red, which means that it's uncomfortable. But it's not so easy to say what is good comfort. So we will have a look at the definition of comfort classes. But when we talk about comfort, it's always somewhere related to the weather file that we use. So I will start with that. Here you can see the TMY file for Uccle, Belgium. And you see that the maximum outdoor temperature is even not higher than 30 degrees. If you compare that to those weather files for the recent 4 years in Belgium, you see that that old TMY file is not representative for the summers that we had, or the last summers that we had. So we decided to build a new weather file, and that came out to be the black line on this graph. So it is based on the most severe heat waves of the last 10 years. And in the meantime, future weather files were built in the framework of the Annex 80. It was based on the Cordex future weather data. And then we see that there is a good match between those future weather data and the data that we used for our simulations. So in fact, we can say that our weather file that we used in the simulations is future-proof. And then coming to the comfort evaluation, here you can see for the terraced dwelling with passive cooling strategies, in black the outside temperature, and then in different colors the internal temperature for different rooms. And then the temperature limits according to SIPSE are also indicated. In green for the night zone, there the maximum temperature is 26 degrees. And then for the day zone in red, maximum temperature is 28 degrees. And then you can see that there are some comfort issues. Especially in the night zone, we have more than 200 exceeding hours. But we are working with extreme weather data, and then we see that there is a tendency to work with adaptive temperature limits. So where the maximum temperature is a function of the external temperature on the x-axis. And when we evaluate the same case with those adaptive temperature limits, we see that all temperature are in category A1, so that means that there is good comfort. When we apply the adaptive temperature limits according to van der Linden, then we see that there is a better match with the fixed temperature limits, because you can see here that we have some temperature here that are not anymore in category A, so here we have some comfort issues too. So if we bring that together in this graph, you can see for all the simulated dwellings, the exceeding hours on the x-axis according to van der Linden, on the y-axis according to the SIPSE, the fixed temperature limits. And then you see that all the cases that are in category A of van der Linden, so with no exceeding hours, that they have less than 100 exceeding hours according to SIPSE for the day zone, and less than 250 exceeding hours according to SIPSE for the night zone. And this brings us to this definition of comfort clauses. So they are all based on exceeding hours according to SIPSE. Good comfort means that they meet the absolute criteria. But then we also defined two comfort clauses based on those limits of 100 and 250 hours that we derived from this graph. So this means that cases that are within category A of van der Linden, they will end up in one of those clauses. And then when we have more than 250 exceeding hours, then we can say, well, it will be discomfortable. So these two clauses helps to avoid false negative ratings of comfort, in fact. And then when we apply that on the case of the terraced dwelling, we can see that for the day zone, we have good comfort. For the night zone, we will have possible comfort, or the orange color. So when we can define our comfort classes, we can go to the next step and look at some general results of the simulations. I will show them with these box plots. So you can see on the x-axis different cooling systems, and on the y-axis the exceeding hours according to SIPSE. And well, the scale of the graphs will change in the next slides, but you can always see those comfort classes, green, yellow and red, as I described before. Then we start with the blue one, that are all the cases without any cooling system. Then here we have our three ventilative systems, adiabatic and the cooling coils with high and low temperature. And then here we have the hydronic systems with the convective systems and the floor cooling. And then here at the left side, we have results for the day zone. At the right side, we have results for the night zone. Here we see that for the cases with no cooling system, 50% has discomfort in day or night zone. So this means that they have exceeding hours more than 250, so they are above the red line. For ventilative cooling systems, this is 40%. But when we go to here to the ventiloconvectors with a capacity of 15 watt per square meters, 80% is in the class of good comfort, so the green class below the green line here. And when we look at floor cooling, it's even better. So when we know that those hydronic systems have a capacity between 15 and 50 watt per square meters, it can seem a bit surprisingly that performance is so good, because we also calculated in the simulations the maximum power that is needed to maintain a constant inside temperature of, for instance, 24 degrees. And for all the cases, it's on average somewhere between 20 and 40 watt per square meters. But the fact of allowing a temperature variance going to 26 or 28 degrees, which are in fact the comfort limits that we used, it lowers the necessary cooling capacity. And that's, of course, very interesting, especially for sustainable cooling systems, because they often have a limitation on their capacity. Then when we look at other building parameters, solar shading appears to have most influence on comfort and on energy use. So here you see the same graphs, but for all cases with external solar shading. And then you see that 55% of all the cases without cooling systems has good comfort now. And when we go to the hydronic systems, we see that in combination with solar shading, all of them have good comfort. And energy use is lowered also. It is divided with 3 approximately. We also see that, of course, in the night zone, solar shading is not that efficient. But we can apply that other passive cooling strategy, ventilative cooling. And then we see that, watch out, the red line for discomfort is here now. So we can see that practically all the cases have an acceptable comfort. They are practically all below the red line. But you see also that in the night zone, when you really want to guarantee a good comfort, so getting below the green line, then you need at least something like a cooling coil at high temperature. And then in general, we can also say that those passive cooling strategies, so solar shading and ventilative cooling, they prove to be much more important than, for instance, the degree of insulation or the inertia of the building. So we can come to some conclusions. First of all, comfort criteria for summer comfort appears to be difficult, especially in residential buildings. Then a combination of passive strategies and sustainable cooling systems is preferable. First of all, in the design phase, cooling loads will be smaller. Then cooling capacity is reduced, so it means that we have more possibilities for emitters at high temperature, and we will have less impact on the electrical grids in summer. And then finally, energy use of cooling can be considerably reduced by using a free cooling source in combination with passive cooling systems.
What a great presentation. I'm a window manufacturer. and I'm a window manufacturer, and we are selling windows and we are selling solar shadings. And this was tremendously interesting what you showed here. I have 2 questions. You mentioned, I think you mentioned somewhere in the end of your presentation that strategies for passive cooling was better than insulation of the building. That was one thing. I just need to go to that phone. That was one thing. And then the other thing I would like to ask is if you have opened the window slightly more than the 15 centimeters that you used in your calculation. I fully understand why you talk about 15 centimeters, because you want to have burglary resistance solutions. But have you tried to include rapid ventilation also for the period where it's hot outside and before you go to bed, to make a rapid ventilation of your home? Have you included such a thing?
Just increase the rates, you mean?
Yes,
Or,
exactly. Yes. Yes.
No, we just worked with the opening of windows, and of course, if at night, if outside it's colder, we open the windows. It was a quite strict regulation of opening when it could cool the room. So in that way, yes. So we have, but we had two options. We had the option with the 15 centimeters. We had also another option where we really opened it with a larger opening.
Okay. And then the first question was about the insulation.
Yes, we saw that for insulation, it can work in different ways. If you have buildings that are critical, where you get high temperatures, because there is no cooling system or no cooling passive strategies, then you see that insulation gets the warmth inside. So there it's not good to have more insulation. But if you have a building with, for instance, intensive ventilation where you have lower temperatures, then we see that insulation can help to temper the influence of outside during a heat wave. It gets the heat outside, in fact, and then you have a different action, in fact, of that insulation. That's one thing. And then for inertia, inertia just on itself, it has not much impact. But of course, if you combine it with that intensive ventilation, then of course it's good to have more inertia, because you need it to get advantage of the intensive ventilation. If you are ventilating at night and cooling down the mass at night, it will have more effects during the day when you have more mass. So in combination with intensive ventilation, okay, but on itself, we don't see a difference.
I would like to take a long discussion here, because there's a lot of interesting topics, and I'm not sure I'm allowed to, but the challenge is that we, during the winter period, insulate buildings extremely, and during the summer period we don't want to have it. In the winter period, we want to have windows to the south. In the summer period, we want to have windows to the north, and of course we can't change those things. I think that what could be relevant to discuss it is how did we solve those problems in the past? If we go back 100 years or something like that, where we didn't have any of the technologies that we have today, there are a lot of good examples on building design and city designs where cities has been developed in order to reduce the risk for overheating during the hot summer period. You can go to some Arabic countries, Southern Europe, Africa, and so on. There are some good examples on how to build, to optimize buildings for summer comfort also. That was a comment, yes. I think.
Okay.
Yeah. Thanks.
Yeah. Thank you. If there are not other questions, I think it's time to go to the next presentation from Ami Amarnath. It's about the same topic, but with a different perspective, a technology assessment to enable consumers to lower energy cost in comfort conditions.
Good afternoon, ladies and gentlemen. My name is Ami Amarnath. I'm a senior technical executive at the Electric Power Research Institute in the United States. Today, I'm going to be talking about the laboratory testing of residential heat pump controllers for demand response applications in Europe. These are the project results from our testing at IREX laboratory in Tarragona, Spain. IREC is the Energy Research Institute. Demand response provides an important solution for grid flexibility. Okay, what's the background for grid to become flexible? The European Union is aiming to be climate neutral by the year 2050 by reducing greenhouse gas emissions. One way to do that is to increase renewables on the grid. So once the renewables are increased, then they need to be increasingly flexible in order to operate appropriately. A cost-effective approach to provide this grid flexibility is to adjust demand-side electric consumption or do demand response on the user side. So what was the project objectives of our project? Our project objectives were to evaluate the capabilities, communications, and controls in smart gateways and controllers for heat pumps for demand flexibility. We want to assess and demonstrate the communication signals, especially new signals called OpenADR 2.0b communication protocol. How well does it work? We wanted to identify commercially available controllers and gateways that can receive such signals and be used for flexible demand response. Finally, if such gateways were available, what are the potential hardware and software options where we can control other residential end users, such as lights, appliances, etc. The laboratory test setup was in IREC Tarragona, like I mentioned earlier. This is a heat pump outdoor unit that was installed in a thermal climate chamber as shown in the photograph on the right-hand side. What we did was a hardware in the loop testing. In other words, there was a computer model developed to estimate heating and cooling loads in residential applications in Spain especially. Water loop temperatures were modified based on these loads. The heat pump was being controlled to address these loads. And the heat pump delivered cooling and heating capacities to the resulting indoor unit. So in terms of communications, okay, how do you communicate signals to a heat pump from the energy service provider? Usually there is a top node called virtual top node, which can send signals. We looked at two pathways. The pathway one was to have an OpenADR virtual top node or VTN to send a signal to an integrated virtual end node or something that receives a signal and a gateway located inside the residential premise. From the gateway is a signal going to the heat pump controller. And of course, from the controller, the signal going to the heat pump to do the appropriate thing by increasing or reducing the speed in order to increase or reduce the amount of energy that is used. So that's one path. The second pathway was to send a cloud-based signal from the VTN to a cloud-based VEN. And then from that VEN to the gateway located inside the residence using a proprietary communication protocol. From the gateway to the heat pump controller again, and from the controller to the heat pump to control the heat pump. So this was the schema that we had to do this testing. The DR signals that were tested were two. Power and emergency curtailment, which is cut the power off completely. Instead of sending these explicit signals, okay. Now, what was the heat pump control logic that we used to control these control the heat pump? For the explicit demand response, it was standard thermostat control with power limitation capability. In other words, it's a rule-based control. For implicit, there was a rule-based control depending on the price. And we also did another implicit DR, which is a model predictive control. In other words, rule-based control is just to reduce energy cost. Model predictive control is to maximize as much comfort as possible by reducing the energy cost too. So, so if one could understand what the price is tomorrow, day after tomorrow, can you take appropriate action today to maximize your comfort? That's really what we try to do. So these were the experiments that we tried. So what did we find? So, we did this both in the heating and cooling markets. Now, for the target power for explicit demand response, the rated power for the unit that we tested was 2.7 kilowatts. The target power with 70% reduction was, or rather 70% of the power to be used, 30% reduction was 1.9 kilowatts. And we came, in fact, our measured power was less than that. Similarly, for 40% of the power use or 60% reduction, we saw and similar results, and even for complete shut-off, we saw similar results. And we saw the same type of results for the cooling applications too. In other words, the measured power was less than or equal to the target, and which in essence tells us that the demand response signals. Okay, I mentioned about implicit DR, which is price-based. Okay, for price-based signals, we did both, rule-based control and model predictive control. For the rule-based control, what we saw was for heating application, 48% reduction in the energy use, and or in the cost, I should say, and for the cooling applications, 58% reduction in cost. The model predictive control also resulted in cost savings, but not as much as this, because remember I said that we got to increase the comfort for the customer. So this is good. The heat pump demand response works. There is some sort of comfort for the customer, and at the same time, the customer can save money. So what does it mean for service provider, for the energy service provider? How can they use this to build new business models? So we thought of two separate business models. One is serving the customer, and second one is serving the grid. For serving the customer, it's the smart home solutions. Or in other words, this energy service provider could supply a smart home energy management system called HEMS, or in the US nowadays, they call it as SHEMS. Okay. And the second one is really to understand, is to build a business on telling the customer on how much energy the customer is consuming and what kind of recommendations they can take to reduce the amount of energy used or to reduce their cost. So one is a service, both are service actually, but one is related to doing the complete home energy management system. I'll talk a little bit more about that. And the second one is to do more of analytics for the customer. Okay, this is on the customer side of the business. From the grid side, an energy service provider could provide the same sort of service to understand how the grid can be flexible and how such demand response can indeed provide support to the grid. In other words, support to both the operation of the grid and also to the transmission and distribution assets of the grid. Okay, and the implicit demand response for optimal time of use controls. In other words, what type of perhaps tariffs can be put in place, or pricing mechanisms or tariffs can be put in place in order to optimize the value for the customer. So these are the different business models we came up with. I mentioned smart home solutions. So if one could essentially think of this gateway that we tested here in this technology, this gateway is connected to the heat pump through a specific protocol. In this case, a Modbus communication protocol. But if the gateway were to be multi-protocol application, then this gateway could also control other things such as lights, such as appliances in the house, all of which have different communication protocols. So it's important to have kind of a multi-protocol gateway that can control not only the heat pump, but also all other equipment. And that will increase the value for both the customer in terms of understanding how much energy different pieces of equipment is using, and also to the service provider in providing the correct solution for the customer. So this is the business model that I talked about. So finally, let me just say in conclusion that our tests showed that the heat pump control technology is a promising technology for demand response applications. The curtailment strategies that we used achieve space conditioning power limitation targets with accuracy, and we could reproduce it. So it works. The rule-based, predictive, and model-based controllers efficiently shifted the loads from a high to a low energy cost periods. So in other words, we saw 48% cost reduction for RBC price in the heating mode and 58% cost reduction in the cooling mode. One important question is, what kind of protocols, communication protocols work? OpenADR 2.0b, which is widely used in the United States, is a protocol that's highly secure communication standards that can indeed be deployed for DR programs in the in Europe. Actually, it's now being developed and applied in the United States in many states. So it could be, tested. We tested the OpenADR gateways, and we saw good signals, good transference of signals to the heat pump controllers. The energy, another important thing that we saw, in fact, I didn't mention this earlier, is energy and power rebound effects were not significant. In other words, once the demand response event is over, is there a rebound? They were not significant, but to really do some good tests, one needs to do field tests with several multiple heat pumps to understand that synchronous dynamics. Finally, as I mentioned, the business model for smart home solutions and grid flexibility solutions, two business models for the energy service providers are good examples of how this can move forward in a business sense. I'd like to acknowledge the following people: Naturgy, which was the project funder, Sylvia Sanvoquin, Alicia Gonzalez, and Nuria Lucas. So these three folks supported us on this project. EPRI was also a project co-funder, and my colleagues Don Shairi and Alekhya Vadiraj worked very closely with me on this project. IREC, where the testing happened, the researchers who worked there, Elena Fuentes, Thibault Pian, and Jaume Salom, they all supported us very well on the project. And finally, I should say that the two gateway providers that I mentioned earlier on, one was Entwined and the other was SkyCentric. The Entwined was the one which is the WEN and the gateway connect inside the home, and the SkyCentric had the WEN in the cloud. Ryan May from Entwined and Tristan D. Fondaville from SkyCentric's providers support on this project. With this, I conclude my presentation, and I'm looking forward to answering any questions anyone may have. Thank you.
I think it was very, very interesting to see this presentation also, and maybe you made a note on all the presentations that we have had today, at least in this session, because if you install your system into the other free presentations we have had before, you would probably be able to help them in reaching the target that they have set and some of the challenges that they have. So I think it was very interesting. One thing that I'm thinking about, which I would like to ask you about, it is that our industry is not that fast moving. The construction sector is very slowly moving at least when it comes to technology, and that is of course because building stands for quite some years, and there's a lot of other technologies that move much faster. Do you think that it is possible to make such a gateway that can bring together all the different components that we have in the building, and also to have it to work for a long period of time? I mean, when I change my washing machine 10 years after I have bought it, it is probably updated with a completely new thing. And do I then need to change my gateway and things like that? Can you elaborate on that?
Sure. Hey, thank you, Kurt. Thank you for the kind comments. Yeah, you're absolutely right in the sense that when you buy appliances and equipment for your house, that asset is there for 15 years, maybe even more. Okay, so it's important to get new technologies, and these technologies will filter in rather slowly. What is interesting about such gateways and the new technologies on demand response is more on the customer value proposition. Okay, when I say the customer value proposition, I think in the previous presentations you heard something about customer comfort. If customer sees comfort, new technologies bringing them more comfort, and at the same time there's not a big impact on the cost, then such technologies will enter the market quickly. Okay, I also mentioned that you can have a smart home solution. Okay, how about integrating such smart home solutions with home security? These sort of new business models where an additional value can be given to the customer, gets these new technologies into the marketplace much faster. I hope that it's sort of like think of it like the iPhone revolution. when it came in, it was kind of did a few things, but now everybody would like to use the iPhone because of the value, or Android phones that provide the value. So it's sort of similar to that. Hope that answers your question, Kurt.
Yeah, I think it's you have a point in that, and it's answering the question, but it's another issue on the multi-protocol gateway, because maybe one of the solutions could be standardization in this field. For example, if I'm going to a smart home solution, if I'm doing now, I don't know much about United States, but in my country, for example, or in Europe, you might be blocked in the technology that you have chosen. So you would connect only some technology and not all the technology. And this has become more critical, I think, if we are speaking about building services, about the heat pump, and about communicating with equipment, not with smart devices or some small equipment in the house. We're speaking about the whole maybe energy management system.
Yeah, another very good point. We, like you can see behind me, we are the Electric Power Research Institute, which is a non-profit public interest research organization. So one of our major goals is really to focus on standard applications, standardization, and in terms of communications using open protocols that signals can be sent through internet and be recognized by any sort of communicating devices on the other side. What's happening in the telephone industry as an example. So those are some of the things that we and a number of other organizations are pushing in terms of standardization. Where we have actually succeeded, to be perfectly candid with you, I mentioned this OpenADR 2.0b communication protocol via the internet. It is a standardized communication protocol that has generally been accepted amongst all energy service providers here in the United States. Okay, so that's where standardization is happening. But then when we come to the end-use devices, manufacturers would like to have their own set of protocols so that they can do other things. They can provide value to the customers, for example, to do, to take care of the unit, to do maintenance of the unit. They'd like to have some sort of a one-on-one communication. An example of that is a smart thermostat that has been developed here by a company called Nest. okay, which does have smart, proprietary communication protocols so that they can communicate directly with the customer. So there's a challenge between standardized open protocol for communications that anybody can use. It can be interoperable. You can switch from one device to another device versus proprietary communication protocols that a lot of manufacturers would like to see because they can grow their business that way. So this has been a sort of a challenge. We're working through it. It's just not EPRI, the United States Department of Energy, the Environmental Protection Agency, through our Energy Star program. We're all working towards standardization. I think that'll happen, but it's going to happen slowly. We have to give opportunities for manufacturers to come up with new technology also. So it's a challenge, but it's happening through groups and organizations such as the ones that I just mentioned. Hope that answers the question, Aurea.
Yeah, but still, do you think it's likely to allow one black box to manage all the devices?
Oh yeah, today as we speak, there are companies. I mentioned two companies. These are not the only two. There are other companies that are developing, what are called as quote unquote multi-protocol converters. And then you say, hey, you have any protocols? It doesn't matter. We can connect with each other. It's somewhat similar to cellular technology. You know what I'm talking about? Whether it is, at least in the United States, whether it is CDMA technology, the TDMA technology versus the 4G technology, which is all interoperable. So, there are companies that are making, at least producing these sort of gateways. But obviously, what is very obvious is the cost will reduce when such gateways are standardized, and there's just one set of communication protocols. Okay. Once again, I got to say that it's still a challenge, but we are working through it because we have to give opportunities for equipment manufacturers to innovate and whatever plans they have, we have to understand those plans.
Okay, thank you very much, Ami, for your clarifications and for the presentation and the whole discussion.
Thank you.
I will just want to come back with the not posed questions to Mark. Mark, if you're still here, it's only a short clarification about the fact that you mentioned in your presentation about a coverage of 40% of the building energy due to the PV, to the photovoltaics. And just to clarify if this is only energy performance of buildings services, or it's also the ancillary, the appliances and everything that the tenants are using?
It's 40% of all electricity consumption, including household electricity, but it's not 40% of energy consumption. The 40% are only for electricity.
Okay, the electricity consumption.
Yeah.
Thank you very much.
You're welcome.
And I will thank everybody, every speaker for the contribution and for this fine session. I would like to say that we are coming to an end in a couple of minutes, but it's more. We will have tomorrow another session. So we would like to invite you to, at the same time as the session today, tomorrow at 2:30 p.m., we will have a session on how to accelerate the route to climate neutral building stock. And also I would like to remind you that in a bit more than 15 minutes, we will have two sessions. On one led by Mr. Paolo Bertoldi from the European Commission, looking at the impact of energy efficiency projects on property values, rents and credit risks. And the other one led by Cédric Jeanneret from SIG, will discuss a concept for pan-European interactive knowledge transfer platform for radical energy savings. Both will take place in 15 minutes, I think, and will be on Zoom meeting mode, so you can join the discussion if you would like to participate. So thank you very much, and thank you, Kurt, for co-leading this session. and
You did the
hope
work.
to see you tomorrow.
Thank you.
Thank you. Bye.
Bye-bye.
Bye-bye. Bye.
Bye.
Bye.